There is a visitor in our sky that breaks the rules, and it is not shy about it. 3i Atlas breathes gas like a comet, yet looks like a perfect point of light, clean and sharp, with no dusty halo at all. How can chemistry shout while the shape stays silent? On October 14th, 2025, a mountain of images told us the tail was missing. Another set of instruments insisted the gas was there. So, what are we looking at? A glitch, a cover story, or a new kind of object? Stay with me, tap like, and subscribe now so you do not miss what we uncover next. Take a breath and picture this. A camera in orbit stares at the same patch of sky for weeks, taking thousands of frames. Astronomers stack those frames to squeeze a whisper into a voice. That process, called image stacking, raises faint glow above the background the way a choir lifts a song. If dust hangs around an active object, the composite should reveal a soft haze spreading outward. Instead, 3i Atlas stayed as tight as a star. The brightness fell off exactly like a point source. No fuzzy edge, no halo bloom, nothing that says ordinary comet. At the same time, infrared eyes told a different story altogether. The James Webb Space Telescope and other infrared instruments do not care about sunlight bouncing off grains. They listen to molecules humming in heat. Water vapor, carbon dioxide, clear signatures of gas leaving the object. It is like standing beside a campfire and hearing the crackle without seeing the smoke. Could a tail be hiding in plain sight because the dust grains are too large to scatter optical light? Could the tail be pointing almost straight toward us so the geometry foreshortens it? These are real possibilities, and we will test them. Yet the deep stack from space should still have teased out some structure if the dust were there in normal amounts. Here is where the story turns from telescope drama into a detective case. Somewhere between the photons and our conclusions lives, the pipeline that turns raw signal into evidence. Detectors have hot pixels and cosmic ray hits. Data get compressed. Headers carry timestamps and pointing info. Archives store and reorganize those files over months and years. If you think this sounds fragile, you are right. If a crucial frame was tagged as a calibration shot and filed under the wrong label, it can vanish from easy search. If a downlink window was missed during a solar storm, those bits may never have reached Earth in full resolution. Before we jump to wild answers, we need a clean chain of custody from the sky to the screen. Now for the part that could crack the case quickly. During its cruise, the Psyche spacecraft carried cameras that take calibration and navigation images. Interplanetary probes do this routinely. You have a working camera in deep space. You test it often. The trajectories suggest windows when 3i Atlas might have been within reach of that imager. If any frames exist, a single clear view could end the argument in a heartbeat. Natural lump with jets, fragment swarm, smooth reflector, one look could separate them. But so far there is silence in the public record. That silence may be innocent. Bandwidth is limited. Data can be queued. Embargo periods exist so teams can analyze first. Still, we should ask for the receipts and we will map that path together. While we push for those receipts, we can work the physics right now. Dust size matters. Tiny grains scatter visible light efficiently and make bright tails. Larger grains, from millimeter to centimeter scale, stay close to the nucleus and scatter poorly. A coma made mostly of those heavy grains would hug the object and look faint in optical bands while gas lines blaze in infrared. Viewing angle matters too. If the sun, the object, and Earth line up in a particular way, any tail can hide along our sightline. Activity can also pulse. A burst seen by one instrument may fade before another takes a look. These effects explain some of the mismatch. They do not yet explain the stubborn sharpness of those deep stacks. So, we will set ground rules right now. No special pleading, no moving goalposts. If later images show a resolved halo that tracks with gas production, the mystery shrinks and the comet story wins around. If high-resolution views keep returning a point-like profile, while spectroscopy screams activity, the paradox grows and more exotic ideas move up the list. Either way, the outcome is a win for understanding. We walk forward with simple questions. What is the shape? What is the timeline of activity? What happens when many instruments stare together? What do the archives really contain? Our investigation is not a passive ride. You and I will treat this like a shared field notebook. We will chase the formal logs. We will compare light curves to gas lines. We will watch space weather so nobody can hide sloppy handling behind a storm. And we will keep the language human. No jargon shield. When a concept needs a name, we pause and explain it in plain words, then move on. That way everyone can track the threads as the plot thickens. Here is the promise. In the next parts, we will unpack the TESS stack step by step, translate infrared chemistry into everyday sense, and show how geometry can lie to your eyes. We will draw a clean map of the Psyche archive trail and lay out the exact tests that could force a decision. Curiosity will lead, but method will drive. The paradox is real, the data are on the table. The story has momentum. Let us chase it to the end. Start with the simplest picture. A space telescope watched the same spot for a very long time and took a river of images. Instead of judging each picture on its own, scientists added them together carefully so real light adds up while random noise cancels out. Think of it as listening to a faint melody on repeat. Every loop raises the volume a little until the tune is clear. If 3i Atlas were throwing off dust the way comets usually do, that melody should have grown into a visible haze around the object. It did not. What appeared instead was the signature of a point, not a smear, not a soft halo, a crisp dot whose brightness falls away with distance the way a star does through a given set of optics. Telescopes have a characteristic blur pattern made by their mirrors and detectors. It is as personal as a fingerprint. When that fingerprint is all you see, the source looks star-like. TESS stacked more than 9,000 frames and still saw only that fingerprint. No extended glow, no faint skirt of light. The result is stubborn. Let us translate the math into ground sense. Noise is wild and jumps up and down. Real signal shows up in the same place across many frames. Add enough frames, and the real thing rises while the noise flattens. That is why deep stacks reveal faint galaxies that single snapshots miss. By the same logic, even a delicate coma should appear if dust is spreading out from the nucleus. The stack is a kind of time machine that pulls whispers out of the dark. Here, the whisper never became a word. You might ask if TESS is the wrong tool for this job. It is designed to find exoplanets by measuring tiny dips in starlight, not to make pretty pictures of comets. Fair, but that actually helps the case. The system is tuned to detect very small changes in brightness with ruthless stability. It watches for faint ripples around dots of light, and it records those dots with tremendous consistency. When such a system reports that the radial fall-off of light around 3i Atlas looks indistinguishable from a star of similar brightness, that is meaningful. What about artifacts? Hot pixels can spike. Cosmic rays can slash a frame with a streak. Detectors can drift. This is why the teams remove outliers, mask bad pixels, and align the images before combining them. This is also why reproducibility matters. The stacked result and the profile analysis can be run by anyone with the Polnox of the NS. Public data. Independent groups can grab the same frames, apply reasonable cleaning steps, and measure how fast the brightness drops as you move outward. The report is not a press release with no receipts. It is a test you can rerun. Picture the brightness profile as a walk away from the center. Each step outward, the light should fade. For a point source, the curve follows a predictable slope dictated by the telescope optics. For an extended coma, the curve bends less sharply because there is extra light off-center. The TESS profile hugs the point source curve. That is the heart of the claim. Not a vibe, not a rumor, a measured shape. Could the coma be there but tucked inside the blur of the optics? That is the next fair challenge. Every telescope blurs a little. If the dust cloud is so compact that it fits entirely inside the core of the optical blur, then the profile would still look point-like. The stack can probe this by comparing the result with nearby stars of the same brightness and by modeling the instrument fingerprint in detail. If you subtract a model star from the target and nothing meaningful remains, you tighten the no-tail conclusion. The teams report that such tests disfavor any normal amount of extended light. Now weigh this against the infrared detections. Molecules sing at longer wavelengths. Gas lines tell you that material is leaving the object. Dust is a different messenger. It is the confetti that sunlight can actually bounce off. If the gas is high while the confetti is scarce, you get a chemical yes and a visual no. Maybe the grains are large and hug the object. Maybe they are made of stuff that scatters poorly in visible bands. Maybe activity spiked and faded between observing windows. We will not wave these off. We will quantify them as we go. It is important to keep the tone honest. No single instrument is the last word. Every instrument has blind spots tied to its design. TESS gives you long, continuous stares and a well-behaved point. Signature, but its spatial resolution is modest. Ground observatories have sharper pixels under adaptive optics, but they fight atmosphere and weather. Space platforms like the James Webb can read chemistry with thrilling sensitivity, but narrow fields and scheduling make wide structural surveys harder. The truth emerges in the overlap, where independent methods agree on concrete features. Here is why this section matters for the larger story. When an object refuses to show a dusty skirt in a stack that should have found it, the burden shifts. Future optical claims of a tail need to clear the bar set by this result. Show a profile that truly bends away from a point. Show that it survives subtraction against local stars. Show that the curve changes as activity rises or falls. That is how we move from press-friendly images to physical understanding. So the TESS takeaway is crisp. The data were taken in long runs, the frames were aligned and added in a way that rewards real structure. The resulting shape looks like a star, not a smeared pebble with a glow. The analysis is public and reproducible. This does not end the story. It starts it on solid ground. Gas can still be real. Dust can still be peculiar. Geometry can still trick us. But any model that hopes to win must pass the point source test that TESS has thrown down. Until then, the paradox stands, and the chase continues. Let us flip the dial from reflected sunlight to heat and vibration. In infrared, we do not look for light bouncing off dust. We listen for molecules that are warm enough to sing. When water vapor stretches and wiggles, it glows at very specific colors of heat. When carbon dioxide vibrates, it does the same. Instruments like the James Webb Space Telescope are built to hear those songs with absurd sensitivity. So when those detectors report strong lines from water and carbon dioxide around 3I Atlas, they are not guessing, they are measuring. Here is the essential contrast. Optical, telescopes judge shape. They ask whether light spreads into a hazy skirt that would betray dust. Infrared spectrographs judge composition and motion. They ask whether any gas is present and how much is leaving per second. One system sketches a silhouette, the other reads the breath. If a comet is alive with volatile ices turning to gas, the breath should be loud, and in these data, it is. Now put the two stories side by side. The optical stack says, point source, no extended halo. The infrared spectra say active, water vapor, carbon dioxide, possibly unusual ratios between them. That last detail matters because different ices wake up at different distances from the sunday. Water needs more heat. Carbon dioxide can escape when it is colder. If 3I Atlas shows a heavy lean toward carbon dioxide compared with classic comets, that hints at an interior that does not match our usual pantry of ices. Different star of origin, different recipe, different behavior when warmed. So why would gas speak up while dust stays quiet? One answer is grain size. If the object sheds mostly large grains, they do not scatter optical light well. They also move sluggishly, sticking close to the nucleus rather than streaming into a long tail. Another answer is chemistry. If grains are coated with stuff that is dark and glassy, they can absorb sunlight rather than scatter it, muting any visible halo. A third answer is the tightness of the coma. If the gas and entrained dust live in a compact envelope smaller than the blur of some instruments, it can evade detection in images while still lighting up the spectrograph. Spectroscopy also gives us motion. When gas accelerates off the surface, the lines can broaden slightly. When sunlight pumps molecules to higher energy states, the emission strengths change in predictable ways. By comparing lines across time, teams can tell if the activity pulses or if it rolls along steadily. Some observations suggest bursts. That would explain why one instrument catches a busy moment while another sees a lull. It is not that anyone is wrong, it is that the object is fickle and the sky schedules are unforgiving. There is also the matter of where the instruments look. A telescope with a narrow slit samples a slice of space across the object. If the gas is clumpy or directional, you can get a strong signal even if the dust is not evenly spread. Imagine watching steam jets from a kettle through a thin window. You might see the plume's chemistry perfectly while missing the wider room. In reverse, a broad camera field can show the room without tasting the steam. This does not excuse contradictions. It explains how they can arise in honest work and why coordinated observations matter. Here is a sanity check for the artificial hype. If a manufactured reflector were faking a star-like dot, could it also fake the molecular lines of water and carbon dioxide? In principle, anything is possible if you are willing to violate parsimony. In practice, the simplest reading is still that real molecules are present and that they come from volatile ices being heated. That does not mean the object is a normal comet. It means the chemistry passes a normal test. The weirdness lives in how that chemistry couples to dust. So what are the next moves in infrared? First, track the gas production rate over time and compare it directly with any optical brightness changes. If the gas doubles and the optical profile remains stubbornly point-like, the paradox deepens. If gas spikes are followed by brief optical softening, we are closing the gap. Second, chase the carbon family. Carbon monoxide, carbon dioxide, and simple organics carry clues about formation temperature in the birth system. A fingerprint that screams cold nursery far from a sun could explain why 3i Atlas acts differently when warmed. Third, spatial mapping. Some instruments can step the slit across the target to build a crude map of where gas is strongest. If all the action clings to one face, that argues for local vents or fresh exposures. If it rings the object like a shell, that argues for many micro sources or a dust blanket that releases gas evenly. Either geometry matters, either geometry also guides deep imaging and visible light. Aim the sharpest cameras at the side that breathes, and you maximize the odds of catching any faint structure driven by that breath. Finally, set the expectation correctly. Infrared detections of water and carbon dioxide do not rescue the classic comet picture on their own. They confirm outgassing. They do not guarantee a tail you can photograph at visible wavelengths. The dust phase is a separate actor with its own physics and its own stubborn habits. The job now is to keep both stories on the same timeline and in the same frame. When gas speaks, we check the shape. When shape shifts, we check the gas. Day by day, window by window. The truth will emerge where the two lines of evidence meet and refuse to diverge. We began with a paradox. In infrared, the object is alive. In visible stacks, it is silent. The way forward is not to choose a favorite story. It is to force them to talk to each other under controlled conditions. That is why the next parts will design exactly that experiment. Many eyes, same hours. Shared logs. If the breath rises and the silhouette stays a star, we enter stranger territory with confidence. If the breath and the skirt finally walk together, we crown a weird but natural comet and move on wiser. Either path is progress. Imagine a lighthouse that always points its beam exactly toward you. From shore, you would swear the light never sweeps. Tails can play the same trick. If the tail points almost straight along our line of sight, the spread collapses into a narrow core and hides inside the blur of the optics. That is our first suspect. Geometry can lie. The angle between sun, object, and Earth decides how stretched a tail looks. At small phase, angles a tail, foreshortens. At larger angles, it fans out. 3i Atlas may have crossed windows when the geometry punished visible structure. Now consider the stuff the tail is made of. Dust is not one thing. It is a zoo. Micron grains scatter sunlight very well and are easily pushed outward by radiation pressure. They build photogenic tails. Millimeter and centimeter grains are heavier, drift slowly, and often linger close to the source. They reflect poorly at visible wavelengths. If 3i Atlas is throwing boulders by dust standards, the scattered light stays compact and dim, while the gas happily sails off and sings in infrared. Chemistry and mechanics decouple. The breath is loud, the confetti is shy. There is also timing. Telescopes do not share a heartbeat. One instrument gets its slot today, another gets a look next week. If the object vents in brief pulses, you can catch a strong gas phase during one window and a quiet optical phase during another. Bursts are not hypothetical. Many comets flare when a crust cracks or a fresh patch rotates into sunlight. A burst can last hours, a scheduling gap can last days. Honest instruments can disagree without anyone being wrong. Let us push each natural explanation until it bends. Geometry first, we can calculate phase angles for every observation. If tail hiding is the main culprit, the optical profile should relax away from a point as the angle grows. If repeated stacks at generous phase angles still look stellar, geometry cannot carry the load alone. Grain size next. Large grains reduce optical brightness, but they also leave traces. They fall behind and form short, stubby features close to the nucleus. Deep imaging should start to pick up a compact glow just above the instrument fingerprint if heavy grains dominate. If not, the dust deficit is real, not just an illusion of size. What about cohesion? Some surfaces can be sintered by heat and radiation over long, cold journeys. When the sun warms them, gas may percolate, through pores without lofting much dust, a kind of gentle breathing through a crust that could produce strong molecular lines with minimal confetti, but even that process tends to peel off fine material over time. The longer the heating continues, the harder it is to keep dust invisible. The paradox should soften with weeks of sunlight. If it does not, the model must work harder. Electrostatic forces add another twist. Sunlight and plasma can charge grains. Near small bodies, charged dust can hover or hop. On airless moons, we have seen hints of this effect at the Terminator, where day meets night. Could a charged environment keep dust close and clumped, muting the halo? Possibly. It would favor a dense near-nucleus cloud that looks point-like unless you have exquisite resolution. A prediction follows. Polarization of scattered light should show unusual patterns if electrostatic sorting dominates. We can test that with careful measurements at several phase angles, which is why polarimetry sits high on our to-do list. There is also bad luck. Not mystical bad luck, just the kind that comes from weather, scheduling, and a restless Sunday space weather can raise noise in detectors and force instruments into safe configurations. Ground seeing can smear faint structure below detection thresholds. If you thread a series of those setbacks through a fast-moving interstellar visitor, you can end up with a patchwork that leans toward no detection, even if a delicate tail was there at times. The cure is redundancy. Many eyes, overlapping hours, shared calibration. Bad luck loses its power when coverage is dense. So where does that leave us? Geometry can hide a tail, but only sometimes and only to a point. Grain size can mute scatter, but it should still leave a compact skirt in deep stacks. Crusted surfaces can breathe gas with little dust, but the effect should evolve with continued heating. Electrostatic corrals are intriguing, but they require telltale polarization and perhaps radio hints from charged environments. Each idea brings a testable handle. That is the key. We are not stuck choosing a story by vibe. We can set traps and see which explanation walks into them. In the next moves, we will line up those traps. Phase angle sequences to punish geometry cheats. Deep imaging to chase compact skirts of heavy grains. Polarimetry to catch charged dust games. Timing campaigns to close the gaps that let bursts hide. If the object is only playing hide and seek, these steps will flush out the tail. If nothing appears even after all that, the natural stories thin out and the stage clears for stranger physics. Either way, the fog lifts. Either way, the picture sharpens. If you want the fastest path to clarity, you ask the camera that was already out there. Psyche is cruising through the inner system with working images that take navigation and calibration pictures during long stretches of deep space flight. Probes do this all the time. Engineers check focus, verify pointing, and grab star fields to keep the spacecraft honest. 3i Atlas crossed the neighborhood while Psyche was awake. The natural question writes itself. Did those cameras look? Start with what we can know without insider access. Trajectories and pointing rules are public. We can pull ephemerides for the spacecraft and for 3i Atlas, then compute when the angular separation dropped into a range the camera could have framed. We can add sun angle constraints and thermal keep-out zones that missions respect to avoid frying optics. We can check typical exposure times, limiting magnitude, and field of view from instrument papers. With those pieces, we can mark potential windows when a short calibration sweep or a navigation frame could have picked up the visitor, even if it was not the primary target. Now, step inside the data plumbing. Deep space missions live on stingy bandwidth. The Deep Space Network assigns communication windows, and every bit competes with every other bit. Health telemetry comes first. Primary science comes next. Calibration frames, engineering snaps, and opportunistic images must wait their turn. Onboard memory is finite and managed as a ring. New data can overwrite old if the pipeline clogs. Compression saves space, but heavy compression can smear faint sources into the background. A navigation frame might be stored, downlinked later, or replaced by something higher priority if the queue backs up. None of this implies a plot. It is simply how survival and science share the same narrow pipe. Suppose usable frames exist. Where would they live? Most planetary mission data flows into a long-term archive so scientists and the public can retrieve it. There are mission mirrors and instrument team repositories while data is being processed and validated. Release can lag if teams are focused on primary targets. Metadata can be messy, especially for calibration products that were never intended as showcase images. A frame that includes 3i Atlas might be labeled with a generic field name, a TESS tag, or a placeholder target. Search engines will not find what headers do not advertise. There are also rules around timing. Missions often grant an exclusive window so instrument teams can publish first on planned science. That is fair. It rewards the people who built the hardware and planned the observations, but navigation and calibration frames that happen to catch a transient object sit in a grey zone. They are not the core science, yet they can be scientifically valuable. The polite move is to ask for them with precision and patience, and to offer co-authorship if the frames prove decisive. Let us list the innocent reasons we still have not seen anything. Window geometry was never good enough, and the cameras could not separate the object from background stars. Camera readout modes during cruise were tuned for bright targets and short exposures, which would underexpose a faint interstellar visitor. Data were captured but compressed so heavily that a compact source is indistinguishable from noise. Frames exist in raw form, but are catalogued under engineering campaigns and need manual curation to surface. Frames were downlinked but are under an internal review clock while the team checks calibration and prepares documentation. None of these are sinister, all are common, and yet, a single clean frame could do more than a month of speculation. A resolved lump with a stubby halo would support heavy grains hugging the nucleus. A faint fan would vindicate geometry and timing excuses. A perfectly symmetric point with no hint of extension even at tight plate scale would push us toward fragment swarms or non-dust scenarios. One picture could sharpen the entire story. So what do? We make a polite technical case. We publish the computed windows with uncertainties so nobody wastes time. We state the imager settings that would have been sufficient, and why. We ask for any frames within a precise time span with full headers and checksums. We request both raw and minimally processed versions to avoid losing faint structure to aggressive filtering. We offer to help with triage by running difference imaging against star catalogues, then hand back candidates for the team to review. We stay transparent and patient because a cooperative path is faster than a fight. Still, we should build a backstop. If nothing surfaces, we verify that nothing was likely to exist. We compare our window maps with spacecraft activity logs that list camera on or off states. We ask for pointing histories that show where the boresight swept during calibration star fields. We check downlink timelines for heavy traffic that might have forced overwrites. If the record says the camera was never pointed helpfully, or storage was full or compression was extreme, that closes the book cleanly. If the record is patchy, we document the gaps without accusation and move on to other tests. There is also a public benefit that goes beyond this one mystery. Clear case studies help future missions plan opportunistic imaging for transient visitors. Small changes make a big difference. A slightly longer calibration exposure, a wider search pattern around a predicted ephemeris, a policy that tags cruise frames with richer metadata even when they are not primary science. The cost is small compared with the value of catching a once-in-a-decade object with a camera that is already powered on. In the end, the Psyche question is about trust and craft. A camera either looked or it did not. A frame either exists or it does not. The honest way to find out is to ask precisely, verify carefully, and accept the answer documented by logs and headers. If we get the picture, we read it with the same discipline we demand from every other dataset. If we do not, we take that constraint seriously and turn the crank on the next experiment. Either way, we reduce uncertainty. Either way, we move. Before a mystery lives on your screen, it is born as a single photon that smacks a detector. That tiny knock becomes an electric whisper in a pixel. Multiply that by countless photons and you have a picture in the making. But the path from whisper to conclusion is long and fragile. If we want answers we can defend, we must respect every link in that chain and test each one. Start with the sensor. A detector is not a perfect sheet of light. It has personality. Some pixels run hot and report brightness even in darkness. Some go dead and never speak. High-energy particles streak through and paint bright slashes that are not stars at all. Engineers map these quirks, flag bad pixels, and remove obvious hits. When you hear about calibration frames, this is part of the ritual. You teach the system to tell sky from scar. Next comes digitizing. The detector's charge becomes numbers. That conversion has limits. If the signal is weak, the rounding of numbers matters. If the signal is strong, bright cores can saturate and flatten. This is where exposure time counts. Too short, and you bury faint structure in the noise. Too long, and you clip the top and lose detail. For a compact object that might or might not have a delicate skirt of dust, the sweet spot is narrow. Good teams bracket exposures and combine them to cover both faint halo and bright core. Now deal with compression. Spacecraft live on lean bandwidth. They must shrink data before sending it home. Lossless compression preserves every bit. Lossy compression throws some detail away to save space. If the algorithm is aggressive, it can smooth subtle gradients where a faint coma would live. That is why raw versions matter. If we only see heavily cooked images, we may be arguing over artifacts of the recipe rather than the flavor of the sky. Metadata is the passport that travels with the picture. It carries the time of exposure, the pointing of the camera, the temperature of the sensor, the settings of the instrument. If those fields are wrong or missing, the image becomes a stray. You cannot line it up with other frames. You cannot measure how brightness changes with angle or time. A mislabeled field can hide a crucial image in plain sight, or make a real feature look like a processing error. Clean metadata is not glamorous, but without it there is no science, only screenshots. After downlink, Archives keep the record. That sounds simple. It is not. Large archives hold millions of files that move across storage systems over years. File paths change, indexes get rebuilt, formats get updated. During any of those steps, a link can break or a header can be mangled. The antidote is provenance and validation. Provenance means you can trace a file from detector to disk with documented steps. Validation means you can prove the file has not changed by accident or intent. This is where a checksum earns its keep. A checksum is a short fingerprint computed from the file's bytes. Change a single bit, and the fingerprint changes. Reputable archives store these fingerprints. When you re-download a file, you recompute the checksum and compare. If it matches, you know you are looking at the same data. If it does not, you stop and find out why. The checksum is not romance. It is a lock on the evidence cabinet. Processing pipelines add another layer. Teams subtract bias frames to remove baseline offsets. They divide by flat fields to correct for uneven sensitivity. They align frames to a common grid. Each step has knobs. Turn a knob too far, and you can wipe away faint structure. Leave a knob too loose, and you let noise masquerade as a halo. The cure is transparency. Publish the steps. Publish the parameters. Show that different reasonable settings lead to the same physical conclusion. That is reproducibility you can trust. There is also the human factor. People are busy. Labels can be sloppy. A calibration campaign can drop frames into a folder meant for tests and never circle back. None of this requires malice. It only requires the usual pressures of limited time and endless tasks. That is why community audits help. Many eyes catch many small oversights. Many hands rebuild chains of custody. When the crowd can rerun the stack and match the profile, doubt fades and confidence grows. So, when we say the test result is strong, it is not only because the curve looks star-like. It is because the steps from photon to plot can be checked, the data are public, the calibration rules are known, the fingerprint of the file confirms it is unaltered. Independent groups can reach the same slope with their own code. That is what turns a headline into evidence. Carry this mindset forward. Demand raw or minimally processed frames when possible. Ask for metadata that can be verified. Check checksums. Try alternate pipelines. Share scripts. If a claim survives that gauntlet, it deserves attention. If it breaks, better to learn now than build castles on sand. The universe is strange enough on its own. We do not need sloppy chains to make it stranger. We need clean ones to reveal what is truly there. When nature refuses to act like nature, you lay every honest idea on the table and ask which ones can survive contact with data. We start with the quietest possibility and climb toward the loudest. At each step, we pin a clear prediction to the wall. Then we see what sticks. First idea, a mostly inert body with microvents. Picture a crust that is tough and sintered from eons of cold. Sunlight seeps in. Tiny cracks exhale gas, but the surface does not shed much dust. Infrared lines light up because molecules are truly escaping, while the visible image stays star-tight because there is little confetti to scatter sunlight. Could that work for a while? Yes. But as heating continues, microvents should grow, crust should flake, and at least a compact skirt should appear in very deep stacks. Prediction. As heliocentric distance shrinks and total gas increases, the optical profile should soften measurably, even if only within a few instrument pixels. If months of heating pass and the profile never budges, microventing alone begins to look thin. Second idea. A fragment swarm that flies in close formation. Imagine dozens or hundreds of small pieces traveling together so tightly that no telescope can resolve them as separate dots. Each piece breathes a little, together producing the gas signature we measure. Optically, the group still looks like a point because the formation is smaller than the blur of the optics. This can mimic a single nucleus for a time, but gravity is weak at this scale. Solar tides and gentle collisions should spread the cloud and imprint subtle shape changes on the light curve. Prediction. Careful photometry over many rotations should reveal tiny irregular brightness wiggles that drift over days as fragments rotate and reconfigure. Deep imaging should also show an elongation that changes position angle with time. If the object remains photometrically smooth and geometrically symmetric, the formation flight story loses fuel. Third idea. Dust that will not leave because electromagnetic forces are in charge. Charged grains can hover, hop, and even corral near small bodies when sunlight and plasma do the sorting. In that regime, gas escapes with ease, but dust grains can be trapped close to the source and remain optically faint. You get a compact, dense shell with little extended scatter. This is exotic for comets, but not alien to physics. Prediction. Scattered light should carry polarization signatures that differ from fluffy comet dust. Radio observations might catch faint bursts or a steady whisper from plasma interactions. Faraday rotation of background radio sources seen near the line of sight could betray a magnetized envelope. If polarimetry looks textbook, cometry and radio checks stay mute across good windows. Electromagnetic confinement slides down the list. Fourth idea, layers and chemistry that bias gas over dust. If subsurface ice lies beneath a sintered mantle, or mixed with unusual salts and dark organics, the gas phase can be rich while the dust remains stubborn. This is a materials science version of the first idea, but with a stronger claim. The object's recipe is simply not like the solar pantry. Prediction. The ratio of carbon dioxide to water and the presence or absence of carbon monoxide across distance should sketch a fingerprint of formation temperature. If that fingerprint screams very cold nursery and remains steady while optical profiles never develop even a compact skirt, this model gains weight. If the chemical mix looks ordinary, it does not. Fifth idea, control by rotation. If one face contains the active vents, and the spin holds that face in a geometry that hides dust most of the time, you can miss a brief tail again and again. This is not magic, just bad luck reinforced by a stable axis. Prediction, a repeating heartbeat in the light curve, coupled to pulses in gas strength when the vented face rolls into sunlight. If we phase the photometry and spectroscopy together, and nothing lines up, rotation cannot be doing the heavy lifting. Sixth idea, the one that makes people sit up straight, an artificial object. A structure with reflective surfaces, active systems, or field generators that confine dust and release gases in ways that mimic natural chemistry, without natural geometry. The honest way to treat this idea is not to wink or flinch. It must carry a heavier burden of proof than the others, and it must make hard predictions. Prediction, geometry that resolves into edges or repeating symmetries when we push resolution with adaptive optics or space imaging. Prediction, spectra that contain compounds or isotope ratios that do not belong to primordial ice. Prediction, time-locked correlations across light, radio, X-ray, or even particle events that look driven rather than chaotic. Without signatures like these, the artificial lane does not advance. Now, stack these ideas against what we already hold. The optical profile from the deep stacks is stubbornly point-like. The infrared chemistry is vigorously alive. Geometry and timing can hide a tail sometimes, but not across every generous phase angle forever. That quickly elevates models that suppress dust production or corral dust near the nucleus. Fragment swarms and electromagnetic corrals lead for now, because they directly attack the shape paradox. Microventing and exotic chemistry trail but are still viable if the profile soon softens. Artificial sits on the bench with clear conditions for when it can enter the field. Notice the pattern. Every idea invites a simple, nearby test. Polarimetry across several phase angles. Long cadence light curves to hunt for non-random flicker. Deep imaging with stacking that pushes inside the optical blur. Narrowband chemistry tracked over distance, not just at one hot moment. Radio checks and Faraday. Rotation experiments when geometry lets the line of sight pass near the object. None of these demand a new flagship mission. They demand design, coordination, and transparency. So here is the plan wrapped into one promise. We will not choose a favorite explanation by mood. We will pick the tests that make each hypothesis either pay rent or move out. If the coma appears, dust wins, and the tale becomes a weird but natural comet story. If the point survives while polarimetry goes strange and radio whispers awake, fields take the lead. If structure resolves into something drawn with a ruler, the conversation changes forever. Until then, we hold curiosity high and standards higher. If we are going to flirt with extraordinary ideas, we need extraordinary gates. Clear thresholds, rules we promise to follow before we let our imaginations declare victory. The goal is simple. Define signals that a skeptic would accept even on a bad day. Then aim the instruments. First gate, shape that refuses to be natural. Nature loves lumps and chaos. Ice and rock accrete, crack, and erode into irregular forms. At high resolution, they look dented and messy. If deep imaging ever resolves 3i atlas into repeated geometry that a rock cannot easily make, straight edges, parallel planes, clean rings, a hexagon that keeps its angles from visit to visit, the needle jumps. This is not about one pixel that looks sharp. It is about consistent structure across independent nights and instruments. Push resolution with adaptive optics and space imaging. Rotate the object. If edges stay edges while the viewing angle changes, the gate opens a notch. Second gate, chemistry that does not belong. Primordial ices and dust have a well-known menu: water, carbon dioxide, carbon monoxide, simple organics, salts and silicates. If a spectrum reveals compounds that demand industry or physics not found in cold birth clouds, unusual alloys, persistent radicals that should break apart in sunlight, isotope ratios far from solar norms, the needle jumps again. This is hard but not mystical. It means securing clean spectra across multiple bands and ruling out contamination from Earth's atmosphere or the instrument. Repeat the detection. Compare with calibration lamps and sky flats. A weird line seen once is a curiosity. The same line seen 3 times by different eyes is a case. Third gate. Choreography across bands. Natural chaos tends to drift. Dust brightens while radio stays quiet. Gas lines grow while X-rays do something unrelated. If instead we see tight repeated timing across channels, optical flicker, radio burst, X-ray flash, even a particle detection within the same small window again and again, we have a coordinated engine, not a campfire. The rule here is strict. Timestamps must be precise. Clocks between observatories must be synced. Chance alignment must be beaten by sober statistics. A single coincidence is not enough. Patterns are: fourth gate, fields and control. Comets do not host organized magnetic structures of their own. If polarimetry of scattered light shows a stable pattern that maps like a designed field cage, and if radio polarization or Faraday rotation of background sources lines up with the same geometry, it signals persistent organization in the plasma around the object. Add any periodic radio emission that tracks rotation with uncanny stability, and you have a system that looks driven. Again, repetition and independent confirmation matter more than any one spectacular night. Fifth gate, provenance of the data. None of this counts if the chain of custody is sloppy. Raw frames with full headers must be archived. Checksums must travel with every file. Version histories must explain every reprocessing step. Calibration scripts and parameter choices must be public so others can reproduce the result. If a jaw-dropping feature appears only after aggressive sharpening or creative denoising, we freeze and go, back to raw. If it survives gentle methods and shows up in different pipelines, we welcome it to the table. Now the skeptic's ladder. At the bottom sits natural. To climb one rung to exotic natural, we would need repeatable polarization oddities or field effects without any geometric shapes or industrial chemistry. To climb the next rung to artificial, we must stack gates. Shape plus chemistry, or shape plus multiband choreography plus verified field control. A single gate half open is not enough. The bar is higher than that on purpose. We also pre-commit to failure conditions. If high-resolution imaging resolves only a lumpy nucleus, with familiar jets, and the optical profile softens as gas rises, we step down the ladder and call it a weird comet. If polarimetry looks textbook, radio stays quiet through coordinated campaigns, and spectra hug the standard pantry, we stop teasing ourselves with exotic lanes, no moving goalposts. The rules we set today are the rules we accept later. This is how we keep wonder honest. We invite surprise but bind it to measurements that survive hard light. We write the thresholds before the headline. We synchronize clocks. We publish our code. We let rivals check our work and we read theirs with the same cold eyes. If 3i Atlas crosses these gates, we will know it for what it is. If it does not, that answer is still a kind of revelation. Either way, the sky wins because the method wins. Every mystery begs for context. To keep our heads clear about 3i Atlas, we should look at another object that already broke our instincts. Astronomers using new wide radio arrays found a source that flashes with eerie regularity. 2 minutes on, 42 minutes off. Then the pattern repeats as if a metronome were buried in the sky. Later, an X-ray observatory stared and found matching pulses in higher energy light, a slow heartbeat across 2 windows of the spectrum. That rhythm does not fit neatly into the boxes we built for. Stars and remnants. What could keep time like that? Magnetars are neutron stars with savage magnetic fields, strong enough to twist space and wring energy out of thin plasma. They pulse. But their pulses are usually quick, measured in milliseconds or seconds. White dwarfs can flare if they have strong fields or feed from a companion. They rotate too, sometimes on minute scales. Yet the combination here, radio and X-ray in lockstep on a 44-minute cycle, strains those templates. You can make a model for any one piece, but the whole tune remains awkward in the hands. Why does this matter for our comet that refuses to look like a comet? Because it reminds us that the universe has more ways to make patterns than we have names for those patterns. The lesson is not to leap to the wildest story. The lesson is to keep the door open while you gather the proof. When a new class shows up, slow radio and X-ray, transients, it forces a pivot in thinking. Our priors are useful until they are not. Curiosity is only dangerous when it outruns discipline. With discipline, it is the engine of better models. Now let us pull the thread that ties this heartbeat to our case. The slow pulsar tells us that organized timing can emerge from magnetic structures and plasma processes we do not fully map yet. It also tells us that multiband behavior can be locked together by a single driver. If fields can choreograph emission in a star-scale system, fields may also sculpt dust and gas near a small body in the inner system, not by the same mechanism or energy, but by the same family of physics. Charged particles, magnetic loops, coherent behavior. The scales differ, the principles echo. Does that mean 3i Atlas is pulsing in radio and X-ray? We have no evidence for that. If those signals existed at detectable strength, someone would have flagged them by now. But the heartbeat source provides a target for our expectations. If we run a coordinated campaign on the comet and see nothing in radio or X-ray while gas rises and falls, that refines our story toward chemistry and geometry without field drama. If we do catch brief radio margins or soft X-ray glints timed to optical changes, then the field-based hypotheses climb the ladder with receipts. There is also a humbler lesson. The heartbeat object was not discovered by a single heroic instrument staring at one place for one night. It appeared because new arrays now survey wide swaths of sky with high cadence, and because follow-up tools in different bands were ready to pounce. That is a blueprint. Big sky coverage finds the oddball. Quick multi-window responses tell you whether the oddball is a new class or a misread. For 3i Atlas, our equivalent is clear many eyes, same hours, honest logs, and the courage to publish null results so the map is complete. We should admit something else out loud. Human brains love rhythm. We are drawn to repeating patterns, and we sometimes draw them where none exist. That is why statistics matter. If we look for coincidences across bands, we pre-register what counts as a hit. We define the time window, the expected false alarm rate, and the number of trials. Then we hold ourselves to those numbers. A pattern that survives that discipline will be worth the late-night message to the world. A pattern that dies under it was never a pattern, just the brain doing what it does. So the heartbeat stands as a lighthouse. It warns us not to crash on the rocks of easy assumptions. It shows us that slow, organized behavior is real in the sky, and that cross-band echoes can be clean as a bell. It also shows us the price of certainty, long watches, careful clocks, and instruments that talk to each other. Carry that mindset forward. If 3i Atlas turns out to be only a chemistry puzzle, we win by proving it with the same rigor. If it hides a hint of field choreography, we will be ready to hear it. Either way, the method is our compass, and the sky is generous to those who measure. Far below the waves of the Mediterranean, a forest of light sensors waits in the dark. On an ordinary day that should have passed without a ripple, a single ghost passed through. A neutrino carrying an energy so huge it makes our best accelerator at the Large Hadron Collider look quaint. Think of the collider's protons like sports cars on a highway. This neutrino blew by as a hyperjet on a separate road, 16,000 times more energetic, and it barely noticed the planet it crossed. That is what neutrinos do. They ignore everything until, rarely, one brushes an atom and leaves a streak of blue light in the detector. Why does one particle matter? Because energy is a signature. To sling a neutrino to hundreds of peta-electron volts, you need titanic engines, supermassive black holes with jets, cataclysmic bursts when massive stars die and leave newborn black holes behind, places where magnetic fields whip particles to near light speed and collisions spit out secondaries that decay into neutrinos. When one of those neutrinos hits our detectors, it carries a return address of sorts. It points back along its path with far less confusion than light, which gets scattered and absorbed. It is a message from the most violent corners of the cosmos. Here is how the message is read. Arrays like the one beneath the sea, or the one buried in Antarctic ice, watch enormous volumes of water or ice for the faint flash that occurs when a neutrino finally interacts. From the geometry and timing of the flashes, software reconstructs a track and an incoming direction. From the brightness and pattern, it estimates energy. Then comes the detective work. Was that direction quiet in gamma rays or loud? Did any known blazar flare around that time? Did any radio observatory see a tantrum from an active galaxy? This is multi-messenger astronomy. Photons speak. Neutrinos speak. Sometimes gravitational waves speak. When they speak together, you learn the story instead of just the headline. So, what could this possibly have to do with an interstellar visitor in our backyard? Not because we think 3i Atlas is firing ultra-high energy particles across space. There is no evidence for that, and the scales do not match, but the method is the lesson. If you want to test wild ideas, you design coincidence checks that are cheap to run and decisive if positive. We can ask neutrino teams to flag any events that arrive from the same patch of sky within tight windows when 3i Atlas shows unusual optical or infrared behavior. We can do the same with cosmic ray arrays and gamma ray monitors. The default expectation is simple: nothing will line up. If it does, we do not shout triumph. We calculate the chance of a false match, then we ask for repeatability. If it lines up again, the story changes. Even a negative result teaches us something. If a strong gas surge produces zero echoes in high-energy logs, it trims the family of hypotheses toward low-energy chemistry and dust mechanics. If a soft X-ray glint appears during a burst of gas, and does so more than once, we lean into plasma processes that occasionally touch higher energies. Evidence is not a binary switch, it is a dimmer. Each coincidence test nudges the brightness toward one interpretation or another. There is also a practical reason to keep these channels open. Neutrino and cosmic ray observatories never sleep. Their data streams roll no matter what any telescope is doing. That makes them perfect partners for timestamps. If a claim later rests on a minute-level timing feature in optical data, you can check whether the clocks agree across independent systems. Healthy science loves independent clocks. We should confront the temptation head-on. When a field is buzzing, almost any distant thunder can sound like a signal. Resist that pull. Pre-register what counts as a coincidence. Set a window in minutes or hours. Set a maximum number of tries. Compute the background rate. Then live with the math. If nothing rises above the threshold, you publish the null result, and you are proud of it because it clears space for better ideas. If something does, you publish the method with it so others can try to break it. If it does not break, you have earned your surprise. The ghost particle is not a mascot for our comet mystery. It is a teacher. It shows how to listen for whispers that cross the universe and still carry meaning. It shows how to triangulate truth when one messenger can lie and another cannot. For 3i Atlas, we keep our eyes on the chemistry and the shape. We also keep one ear to the deep waters and the deep ice, just in case the universe decides to speak in more than one voice on the same night. If it does, we will hear it. If it does not, that silence is its own kind of clarity. The sun is not a quiet neighbor. When it hurls a coronal mass ejection toward Earth, 1 billion tons of magnetized plasma race across space and punch our magnetic shield. The result is a light show at high latitudes and a headache for instruments that rely on clean, stable skies. If you are trying to measure a faint haze around a point of light, space weather can turn your careful plan into a guessing game. That does not mean the data are useless. It means the logs must be clean and the analysis must respect the fingerprints that storms leave behind. Start on the ground. The upper atmosphere becomes choppy during geomagnetic storms. Radio waves wiggle and fade. Optical backgrounds rise as airglow brightens. Long exposures collect extra speckles and faint streaks from charged particle hits. A delicate tail can drown in that noise if you do not calibrate it away. Good teams respond with shorter exposures, more frequent sky flats, and careful masking of cosmic ray trails. They publish the sky conditions and magnetometer readings with the images so that anyone can judge how much the storm mattered. Move to space. Detectors above the atmosphere do not fight twinkling, but they do fight radiation. Solar energetic particles can flip bits in memory, pepper images with bright pixels, or push a spacecraft into a quiet, safe mode until the storm passes. When that happens, there are signatures. Engineering logs show spikes in particle counters. Telemetry records show mode changes. Exposure lists show gaps or aborted sequences. Honest pipelines show those events plainly. If instead a release blames generic space weather without matching logs, caution rises. Here is a practical rule. Space weather problems rarely look like smooth, repeatable structure. They look like spikes, streaks, and glitches that do not line up between frames. If a claimed halo survives storm times and quiet times with the same shape and the same scale, it probably is not a storm ghost. If a claimed feature appears only during the loudest hours and vanishes the next night, you demand stronger proof before you call it comet dust. Timing can create traps. Say an instrument scheduled a deep stack during a predicted window of elevated activity. The team did their best. They filtered, masked, and stacked. Still, the residual noise is higher than usual. If another instrument then looks a day later during calmer conditions and does not see the same structure, The disagreement may be environmental rather than physical. That is why redundancy matters. Overlapping observations turn weather into a nuisance rather than a verdict. There is also the temptation to use storms as a blanket excuse for missing data. Sometimes the excuse is true. Downlink windows can be lost when ground stations battle the weather or when spacecraft prioritize health over science. Sometimes the excuse is lazy. A generic mention of a storm covers gaps that actually come from scheduling conflicts or processing delays. The fix is simple. Ask for specifics. What hours were affected? What particle rates were recorded? What thresholds triggered safe mode? What images were flagged? And why? When those answers come with numbers and plots, the conversation becomes science. When they do not, it becomes rumor. For our stubborn visitor, space weather is both a complication and an opportunity. A complication because any marginal tail could be easier to miss when charged particles raise the noise floor. An opportunity because storms are predictable enough that we can plan around them. We can book multiple instruments across longitudes for the same night. We can schedule follow-up on the first calm window after a storm to check whether a feature persists. We can pair optical campaigns with radio monitors and magnetometers to document the environment in real time. Transparency is the currency that buys trust. Publish the weather context with the images. Share the particle counts and instrument states. Note the times when the satellite was in safe mode and when it returned. If an analysis removes a fraction of frames for quality, say how many and show why. These are not burdens. They are the normal costs of doing careful work during a lively Sunday. So we will treat noisy skies as part of the map, not a mystery. We will not accept vague hand waves about storms, and we will not overreact to every glitch. We will look for features that survive changing conditions and for claims that carry their own weather reports. When the aurora dance fades and the instruments settle, what remains in the data will be the signal we can trust. That is the only light worth following. Here is how we turn curiosity into a working investigation. We stop waiting for perfect releases and start building a toolkit that anyone can use. The goal is simple. Reproduce what can be reproduced. Request what must be requested. Cross-check what others will miss. When this is done in public, answers arrive faster and rumors die sooner. Start with where the object is and when it can be seen. Ephemerides are the roadmaps of the sky. With them, you can predict where 3i Atlas will drift hour by hour and how bright it should be under simple assumptions. Use those predictions to schedule overlapping observations across longitudes so there are no gaps when dawn or weather ends a session. If you have access to even a modest telescope, photometry is within reach. Take a sequence of short exposures to avoid saturation. Keep the cadence steady so you can stitch a clean light curve. Calibrate against nearby comparison stars whose brightness is stable. If many small rigs repeat the same sequence, their curves can be stacked just like images, revealing faint wiggles that a single observer would miss. Next, build an image pipeline that is gentle and transparent. Start from raw or minimally processed frames whenever possible. Subtract bias and dark frames. Divide by flats that capture vignetting and dust on the optics. Align on the stars. For a moving target, shift and stack on the predicted motion, so the object stands still and the stars trail. Then reverse it as a check. If a faint halo is real, it will cling to the object in the moving stack and smear in the star stack. Publish both results, not just the prettier one. Post the scripts that did the work so others can run them and compare outputs on their own data. Profile the light. Draw a radial curve from the center outward and compare it to nearby stars of similar brightness taken in the same conditions. If your curve bends less sharply, you're seeing extended light. If it hugs the stellar curve, the object is point-like at your resolution. Repeat on multiple nights and at different phase angles. Small differences can be swamped by noise in a single session, but grow meaningful across a dozen sessions. Keep a log of seeing, sky brightness, and any stray clouds that passed. Those notes will rescue you when a profile looks odd and you need to rule out weather tricks. Spectroscopy for amateurs is not a fantasy. A simple grating can separate light into colors strongly enough to catch bright emission from gas if the object surges. If you can capture narrow features cleanly, timestamp them precisely. Share those times with images so they can check whether profiles softened near the same moments. Even a null result is useful. A night of strong profiles with no obvious gas lines trims the story. For the deeper data hunt, organize a small group to mine public archives methodically. Divide the work by time windows and by instruments. One team pulls every frame from a spacecraft camera during a week when geometry was favorable. Another team scrapes ground observatory indices for engineering frames that match the field. Everyone records the checksums and the exact search terms used, so the search can be repeated later. When candidates appear, difference imaging becomes your friend. Subtract a clean star field taken months earlier from the new frame to highlight anything that has moved. A faint dot that steps across several frames at the predicted rate is gold. Do not keep it in a private chat. File a short public note with coordinates, times, and the method you used. Invite others to break it. Document everything, like a lab. Each plot should carry the date, the instrument, and the pipeline version. Each figure caption should say what was done in 1 or 2 clear sentences. If you threw away frames, say how many and why. If you tried 3 settings for an alignment parameter, show that the choice did not flip the result. This is not busy work. It is how you keep your future self from arguing with your past self when a reviewer asks a sharp question. Build a dashboard that anyone can check nightly. Ephemeris position, phase angle. Predicted brightness range, latest stacked profile compared to stellar controls, last reported gas measurement with uncertainty, space weather indices from the same hours, radio monitoring status if any array is listening. A good dashboard turns a scattered effort into a shared brain. It also makes it easy for journalists and newcomers to follow along without misunderstanding the state of play. Be generous and careful with credit. If a frame from a mission archive becomes central, list the instrument team prominently in every post. If an amateur's stack sharpens a point, ask permission to reuse it and keep their name attached. Invite disagreements in the open and treat them as tests, not fights. Nothing improves a pipeline faster than a polite critic with their own data. Finally, decide in advance how to announce a real change. A softened profile detected by 3 independent stacks on the same night. A polarimetry curve that deviates decisively from comet dust at 2 phase angles. A repeatable light curve modulation that beats in sync with a gas surge. Write the criteria now. When they are met, publish with the raw files, the scripts, and a clear explanation of the statistics. If they are not met, publish the null. That discipline will save time and protect trust. This is the playbook. Predict, observe, stack, profile, share, audit, repeat. Whether 3i Atlas reveals a shy dust skirt or refuses every natural script, the crowd can carry the investigation with standards that match big science. The mystery does not need more hot takes. It needs more clean plots and open files. That is how citizen forensics earns its name. Light does not just brighten or dim, it can also line up its electric wiggle in a preferred direction. That alignment is called polarization, and it carries secrets about the stuff that scattered the light. Think of sunlight bouncing off a field of snow versus a lake at sunset. Your sunglasses help because the glare from the lake is polarized. Telescopes can do a similar trick with far more finesse. They can measure how much the light from 3i Atlas is polarized and how that polarization changes with color and with geometry. Hidden inside those numbers is a fingerprint of particle size, texture, and even the presence of smooth plates, or fluffy clumps. Here is the core idea in plain steps. Unpolarized sunlight hits a cloud of particles. The angles of scattering and the shapes of the grains decide how much of that light leaves in an aligned state. Tiny, airy aggregates tend to produce one curve of polarization with phase angle. Compact icy crystals produce another. Dark, glassy grains shift the curve again. If the light bounces off a smooth surface, such as a metallic plate or an ice face, you get a spike in a particular direction that looks nothing like dust spray. By sweeping phase angle over weeks and measuring at a few well-chosen colors, you can draw a curve that either looks like comet dust or does not. Phase angle is simply the triangle made by the sun, the object, and us. When that angle is small, we look almost straight down the tail if one exists. When it is larger, we see the side view. Polarization grows and fades as that angle changes. In classic comets, it follows a family of shapes that have been mapped for decades. That lets us use a cheat sheet. If 3i Atlas sits on that family, the natural story strengthens. If it wanders off into a shape that refuses to match, we ask why. Bigger grains, odd coatings, a compact near-nucleus cloud, or a surface that behaves more like a plate than a pile. There is also direction, not just amount. Polarized light has an angle on the sky. Imagine drawing little arrows pointing the way the electric field prefers to vibrate. In a normal coma, those arrows line up in a pattern set by simple scattering. If the arrows twist in ways that suggest organized fields or a smooth reflective face, that is a hint of structure. Pair that with color. Dust that is rich in carbon tends to mute polarization at some wavelengths. Clean ice does something different. Metal does something different again. The mix of angle and color forms a signature far more diagnostic than brightness alone. We can do this now. Large ground telescopes carry polarimeters that can measure, down to a tiny fraction of the total light with care. Smaller observatories can contribute by repeating the same measurements at many phase angles to build the curve. The key is calibration. Polarimetry punishes sloppy optics. Any internal reflections inside a telescope can fake a signal. So teams spin calibration polarizers, take sky flats at several rotations, and observe standard stars with known polarization. When the calibration is clean, the data sing. When it is not, everything sounds like noise. What do we expect if the dust is simply heavy and hugging close? The curve should still look comet-like, just shifted toward lower total polarization because the particles are larger and darker. What if electrostatic games are corralling grains near the nucleus? Then we may see a sharp angle pattern that rotates with the object or changes as solar wind conditions change. What if the surface includes smooth plates or engineered facets? Then at certain angles you can see a pop in polarization that is hard to fake with random clumps. None of these hints prove anything on their own. Together, they become pressure on a story to match the map. We can also fold polarization into deep imaging for a 1-2 punch. Take a stack that reaches down to the instrument blur, then map polarization across the tiny glow. If the arrows swing around the nucleus in a smooth and predictable way, dust rules. If they lock to a line or to a repeating geometry as the object rotates, design or organized fields step forward. Add time. Repeat at different phase angles, and watch whether the curve slides along a known family or bends into a shape that lives alone. There is a final gift in this method. It does not need a spacecraft flyby. It needs patience, careful calibration, and a calendar. We can start with the next dark run. We can publish the curve as it grows and invite others to overlay their points. If the plot lands on the comet family, we will say so plainly and move on with better constraints. If it refuses to land anywhere familiar, we will know that too, and we will have earned the right to push stranger models higher up the ladder. Either way, the light itself will have told us about the surface we cannot yet resolve. That is the quiet power of polarization. It lets the hidden surface speak. If polarization is how the light whispers about texture, deep imaging is how we press our face to the window and try to see shape. The goal is simple. Push resolution until a supposedly perfect point betrays any hint of extension, then push sensitivity until the faintest skirt around the nucleus shows itself. This is not about pretty pictures. It is about physics hiding one step below our current blur. Start with adaptive optics on the largest ground telescopes. Turbulent air turns stars into jelly. Adaptive optics measures the warping in real time and bends a flexible mirror to cancel it out. The result is a point spread that narrows toward the hard limit set by mirror size and wavelength. On a 10-meter class telescope, you can chase details that once required space. Pair that with short exposures to freeze the air, then align and stack thousands of frames so the object sharpens while random noise melts away. Lucky imaging by professionals looks like magic. It is just persistence plus math. Now stack with intent. There are two natural alignments. Align on the stars and let the target drift. That reveals background structure and lets you model the instrument's fingerprint with nearby point sources. Then align on the object and let the stars streak. That maximizes any faint glow bound to the nucleus. If a skirt exists but hides inside the ordinary blur, this two-step dance teases it out. Subtract a scaled star profile from the target and watch what remains. Real extension survives subtraction as a gentle shoulder. Artifacts vanish. Color matters. Gas emits at specific colors. Dust reflects a broad spectrum. If you switch between filters that isolate a gas line and filters that ignore it, you can separate chemical glow from scattered sunlight. Take a sequence in a dust-friendly band and in a nearby band that includes a strong gas feature. Subtract the gas band from the dust band after matching seeing and scale. Residual light points to dust. Do the reverse and you map the gas. The point is not a gallery image. The point is a clean yes or no on the presence of extended dust. Difference imaging is your third tool. Build a template of the field from a night when the object was absent or far away. Warp the template to match each new frame. Subtract. Stationary stars cancel. Imperfections mostly cancel. Anything that moved shows up clean. If the object carries a tiny fan, it appears as an asymmetric patch near the core after subtraction, even when the full frame looks star-like to the eye. This is how surveys find asteroids in oceans of starlight. It works just as well here. Spacing and cadence matter too. Repeat deep imaging at multiple phase angles so geometry cannot hide the truth. If the tail points along our line of sight 1 week, it should flare sideways a few weeks later as the triangle between Sun, object, and Earth opens. If extension never appears, even as the angle grows kindly, geometry stops being an excuse. Tight scheduling during the same rotation phases also helps. If vents live on one face, structure should recur when that face returns to sunlight. No recurrence means either no vents or vents so evenly spread that they behave like a shell. What would a success look like? A profile that bends away from a control star by a small but repeatable amount. A residual glow after point spread subtraction that is stable night to night and grows when gas production grows. A tiny fan that points in the expected anti-solar direction and rotates as the geometry changes. None of these require heroic leaps. They require patience, clean calibration, and several nights of calm air. What would failure look like? A profile that never softens even when gas rises. Subtractions that leave nothing but noise, shoulders consistent with the instrument. Filters that refuse to reveal dust no matter how gently you process them. Difference images that show a moving dot and nothing else. Failure in deep imaging is not defeat, it is a hard constraint. It tells us dust either is not present in expected amounts, or is so confined that only more exotic stories make sense. Space telescopes can add the final shove. They do not fight the atmosphere, and they carry stable optics that make point spread subtraction brutally clean. Even short programs can help. A handful of well-timed images across 2 filters can set limits that groundwork cannot reach. If a compact halo exists at a size smaller than ground-based blur, space will catch it. If space does not, the weight shifts decisively away from classic dust behavior. There is one more play. Marry deep imaging to polarization mapping in the same session. Take a sharp stack. Then measure polarization across the residual glow. If the pattern follows the simple scattering expected of dust, natural explanations breathe easier. If the pattern locks to a line or holds a geometry that rotates with the object, like a rigid frame, the case tilts toward organized fields or structure. Deep imaging is the make or break step because it speaks directly to the paradox. Gas without visible dust is a story told in numbers. A faint halo or a stubborn point is a story told in shapes. When shapes agree with chemistry, the mystery ends. When they refuse, the mystery clarifies. Either way, the camera does not care about hype. It sees what is there. Our job is to give it the best chance to see and to read the result with discipline, not desire. One instrument at a time tells you a chapter. Many instruments at once tell you the plot. If we want to end arguments about 3-eye atlas, we need a night when eyes across the spectrum stare together and keep the clocks honest. That is the coordination test. It is not glamorous. It is logistics plus patience. But when it works, it turns speculation into a clean yes or no. Begin with a shared calendar and ruthless timing. Optical imagers line up deep stacks in dust-friendly bands. Infrared spectrographs lock onto the strongest water and carbon dioxide lines with high cadence, not once per night, but in repeating sequences so we can track rises and dips. Radio arrays reserve a narrow piece of sky for fast sampling to catch any brief plasma burps. X-ray instruments set short snapshots in a daisy chain through the night. Particle observatories do not need to schedule. They will listen regardless. Everyone agrees on synchronized clocks and publishes their time offsets in advance. That way, a blip at 2 minutes past the hour means the same thing in every log. Define the targets before the first photon. We are not fishing for miracles. We are testing very specific joints in the story. If gas rises by a clear factor and the optical profile still refuses to soften, the dust deficit is real. If a softening appears in step with the gas, geometry and grain size regain credibility. If radio or X-ray activity pops exactly when gas and optical brighten together, electromagnetic models grab the microphone. If nothing moves together, we tame the exotic lanes and focus on chemistry and timing quirks. The test does not demand a dramatic night. It demands a readable one. Cadence is everything. Short integrations stacked into minutes give us a heartbeat without drowning in noise. Long, sparse exposures give us postcards and miss the dance. For optical, think many short frames with immediate quality checks so bad seeing or satellites are tossed in real time. For infrared, think rolling windows that step through key lines and return, building a pattern rather than a single snapshot. For radio, think sub-minute bins to catch bursts that would be invisible in half-hour averages. Everyone agrees to. Keep a small buffer, so triggers can prompt a quick pivot if something wakes up. We also need a rule for nulls. Coordination is not only about catching fireworks, it is about proving independence. If gas drifts upward over hours, while optical profiles stay flat and radio remains quiet, That independence is a result. We publish it with the same pride as a correlation because it slices away whole families of dramatic ideas. That takes discipline. It is tempting to bury quiet nights. Do not. Quiet nights are the backbone of the decision tree. Data handling can break a beautiful night if we are sloppy. Every team writes down the exact pipeline version they will use. Everyone saves raw frames and minimal reductions, not just the pretty stacks. Everyone posts a preliminary plot and the time series within 24 hours, even if the axes are ugly. That is how the community knows whether to repeat the setup on the next window or change tactics. Within a week, groups rerun each other's data with alternate pipelines to make sure the apparent correlations are not artifacts of a smoothing choice or a filter mismatch. If a correlation survives 2 pipelines, it is real enough to matter, a word about statistics. With many channels buzzing, it is easy to find a coincidence after the fact. So we pre-register. We declare the time window that counts as together and the number of tests we will run. We compute the expected false alarm rate. Then we obey the math. If a brightening in gas and a softening in the optical profile overlap within the window twice in a night, and the false alarm probability is comfortably small, we call it a correlation and move to the next step. If not, we resist story time and log the disappointment. Science advances on disappointments that are clearly recorded. Success looks like clarity, not necessarily drama. Best case for the natural lane, gas and dust walk hand in hand and radio stays dark. Best case for the field lane, optical softening, and gas spikes arrive with timid radio murmurs or X-ray flickers more than once. Best case for the strangest lane, structure appears in deep imaging as polarization locks to a pattern and radio pops on cue. In each case, the evidence stack points one way and the other explanations run out of room. There is a bonus. A coordination night is also a rehearsal. It teaches the network how to move fast together for the next anomaly the sky throws at us. It forges habits that endure beyond this one mystery: shared clocks, quick plots, public logs, and pride in nulls. That culture is worth as much as any single result. It makes future truth cheaper to buy, so we will set the date, publish the plan, and invite every instrument that can play. We will accept the mess of juggling time zones and weather, because the payoff is a clean map of cause and effect. When the night ends, we will not argue about what might have happened. We will read the aligned logs and see what did. If the story points to ordinary physics dressed in unusual clothes, great. If it points to organized behavior we cannot dismiss, we will be ready for the next tests. Either way, the coordination test trades hunches for history. If you cannot draw the outline, you can still feel the shape by watching how the light flickers. Rotation turns a small body into a slow lighthouse. As different faces catch sunlight, brightness rises and falls. That pattern is a light curve. With patience and clean timing, a light curve tells you whether the object is stretched like a cigar, squat like a potato, or oddly smooth in a way that should not happen naturally. Start with cadence. You do not need massive mirrors to measure a flicker. You need steady exposures and stable reference stars. Take many short frames, so clouds and seeing do not smear the signal. Calibrate them carefully. Then measure the brightness of the target against a handful of nearby stars that do not vary. Stack the points into a timeline. The human eye wants to trace a rhythm. Let the math confirm it. Algorithms search for periods that make the curve line up on itself. If a clean period appears, you have a rotation clock. What does the shape say through that clock? A very elongated body tends to swing brightness by a wide margin, as it presents a broad side and then a narrow edge. A nearly round body flickers gently, if at all. Tumbling bodies do not keep time well. Their curves warp and wander as 2 rotations beat against each other. Comet nuclei often sit in the messy middle. They wobble. They sport vents that pulse when a patch of ice turns into sunlight. That creates small humps and kinks on top of the basic rise and fall. Natural is usually messy. Now imagine the opposite. A curve that is smooth like a metronome, a period that holds to the minute for weeks, a waveform that looks almost sinusoidal with barely a ripple. That would be unusual for an irregular lump of rock and ice, especially one that vents gas. It would suggest either a shape and spin axis that conspire to hide irregularities, or something more controlled than rubble. The burden of proof would rise, and we would lean on other tools to cross-check, but a suspiciously smooth curve would be a red flag worth waving. Light curves also talk to gas. If spectroscopy shows a burst in water or carbon dioxide at specific times, and the brightness shows a repeatable bump a little earlier or later, you can tie vents to faces. The delay between sunlight hitting a patch and gas reaching peak intensity carries information about thermal inertia and depth. If the same phase of rotation links to surges again and again, you are mapping geography without seeing it. If gas surges at random with no rotation link, the vents may be everywhere, or the surface may be flaky enough that fresh cracks dominate. There is a geometry trap here too. If we view the object almost along its spin axis, brightness changes shrink even for a very elongated shape. You can mistake a cigar for a sphere. The way out is to watch over weeks as the viewing angle shifts and to combine light curves with polarization. A rotation-linked swing in polarization can reveal shape even when brightness stays steady. Two senses are better than one. Noise is the enemy of small modulations, so we fight it with many eyes. A global ring of small telescopes can hand off the target from time zone to time zone. That gives near-continuous coverage over full rotations. It also reduces aliasing, the trick where gaps in data create fake periods. With continuous coverage, the true period wins cleanly, and minor harmonics stand out instead of confusing the story. Simplicity is the rule for analysis. Use the same comparison stars. Keep exposure times fixed when you can. Record seeing and sky background. If you change anything, mark the time and explain the reason in the plot caption. Then, share the raw photometry so others can refit the period and test for artifacts. A rotation claim is only as good as the timestamps that support it. What are we hunting for? A period and amplitude that say elongated or round. A pattern of bumps that repeats with the clock and matches gas behavior. A lack of chaos where chaos should live. Any of these tilts the scales. If the curve is a natural mess, we accept it and tune imaging to the phases when vents face us. If the curve is strangely perfect, we raise an eyebrow and bring in deep imaging, polarization maps, and radio checks to see if control extends beyond brightness. Rotation turns a distant point into a story about shape, texture, and behavior. We do not need to touch the surface to learn its habits. We need steady watches, honest logs, and clocks that agree. Do this well, and the curve will sketch a silhouette we cannot yet draw. Do it together, and the sketch will be sharp enough to matter. We have tools now: polarization to fingerprint particles, deep imaging to hunt for skirts inside the blur, coordinated nights to force chemistry, and shape to talk at the same time. Light curves to sketch the hidden outline. With that kit in hand, we can revisit every non-comet idea and ask it to pay rent. Each candidate must predict something concrete that we can measure soon, not someday. Start with the quietest story, the microvent world. A tough crust exhales through hairline fractures, shedding gas but almost no dust. What happens when we measure carefully over weeks? Gas production should ramp as sunlight digs deeper, and the optical profile should soften just a little, as weak jets peel away fine grains, not a grand tail, but a measurable shoulder after point spread subtraction. Polarization should land in the comet family, only muted. The light curve should show small repeatable bumps when an active patch rotates into the Sunday. If gas rises while the optical profile and polarization refuse to budge across generous phase angles, microvents alone can no longer carry the load. Now the flock of fragments. A compact swarm can look like one dot, breathe like many, and keep dust confined by weak mutual gravity for a time. The swarm predicts quirks you can chase. The total light should wobble in a slightly irregular way as fragments occlude one another and reconfigure. The orientation of subtle elongation should drift over days as the group's center of light shifts. Polarization could look a bit off, not because of exotic surfaces, but because many small comae overlap into a compact envelope. Deep imaging should eventually catch a peanut shape or a skinny smear in the residual after you subtract a stellar fingerprint. If the light curve stays metronomic and deep residuals stay round, the swarm runs out of air. Electromagnetic corral next. Dust is present, but fields keep it close and organized. You should see polarization patterns that do not fit fluffy grains, perhaps a stable axis in the polarization angle that rotates with the object like a skeleton under the skin. The optical profile may stay point, like, yet a hair wider than a star, in a way that does not change when seeing changes. Radio patrols might catch faint, narrow bursts when the sun's wind sweeps past or when the rotation aligns a structure. A field cage also predicts sensitivity to space weather. During heightened solar conditions, the pattern should twitch or strengthen. If polarimetry lands squarely on the comet curve and radio stays silent over multiple well-timed nights, the corral shrinks to a curiosity. Exotic chemistry is less a shape model than a pantry problem. A composition skewed toward carbon dioxide or carbon monoxide could pour gas without much dust if the upper layers are sintered or depleted in fine grains. This path demands a clean chemical fingerprint over distance. As the object recedes and cools, carbon dioxide lines might linger while water fades, or the reverse depending on the layering. Polarization would still resemble comet dust if dust exists at all, just at lower amplitude. Deep imaging might reveal a compact skirt only in filters that dodge gas lines. If spectra look ordinary, and yet the optical profile never softens, chemistry alone cannot explain the stubborn star. Rotation control tries to thread geometry forever, vents on one face. A spin axis and viewing geometry that hide the dust again and again. This is the most fragile story. It predicts a strong, stable rotation period and phase-locked gas pulses. It predicts that when the phase angle changes favorably, a fan finally appears for a few rotations and then vanishes as the axis tips. It also predicts that deep imaging timed to the active phase will catch an asymmetric shoulder, even if stacks at random times do not. If the phase angle opens and nothing appears, and if gas pulses refuse to line up with light curve phase across several cycles, rotation falls apart, then the one that makes your chest tighten, artificial. A structure that reflects like a perfect point while managing gas and dust with design rather than accident. This model must do more than shrug at contradictions. It must call its shots. Resolved edges at the limit of our best images that keep their angles as the viewing geometry changes. Polarization that pops at specific phase angles the way a plate or facet would. Multi-band choreography that is too tight for chance, repeating over nights with clockwork timing. Perhaps even Faraday rotation signatures mapping a persistent field geometry that looks engineered rather than turbulent. If any of these appear once, we slow down and check our biases. If they appear repeatedly across independent teams and pipelines, the center of gravity moves. How do we choose between these futures without getting lost in maybes? We work the matrix. For each idea, we list near-term tests and their expected outcomes. Microvents profile, shoulder growth tied to gas, fragments irregular light curve and drifting elongation. Fields non-comet polarization and environment sensitivity. Chemistry stable spectral ratios that explain a dust deficit while allowing a compact skirt in dust-friendly bands. Rotation phase-locked gas with episodic extension at favorable geometry. Artificial stacked signatures that defy natural families across shape, spectrum, timing, and field. Then we run the tests in parallel instead of serial. While polarimetry teams map the curve over several phase angles, deep imagers hammer the residuals, spectroscopists track carbon families nightly, and small telescopes knit the light curve into a near-continuous band. Coordination nights anchor the overlaps. The logic is ruthless. Each result either removes a lane or pushes it forward. We should prepare ourselves emotionally for the most likely outcome. Nature usually wins with a twist we did not expect. A crust that breathes without much dust, hardened by an alien recipe. Heavy grains that huddle too close for casual imaging. A rotation axis that makes geometry unfriendly more often than not. A field effect that is subtle but real. The cocktail may be new even if the ingredients are not. That is still a discovery worth cheering. But we should also promise not to blink if the data cross the gates we set. If edges hold, if polarization misbehaves across repeatable angles, if multi-band timing locks like gears, we will follow the evidence to the end of the road, no matter how strange the signpost reads. The sky does not care what story we prefer. It only cares how carefully we listen. We have the ears now. Let us use them. Yes, evidence is not just numbers and plots. It is also custody, consent, and consequence. If 3i Atlas forces us to consider anything beyond a quirky comet, the conversation will vault from charts to charters. Who owns the frames? Who decides when they are released? Who verifies them? And how do we maintain trust when the stakes leap from an interesting object to a potentially historic claim? This is not bureaucracy for its own sake. It is the scaffolding that keeps truth upright when emotions get heavy. Start with data control. Space missions are paid for by public money, but governed by mission charters that grant teams a period of exclusive access. That is fair. People who built the hardware deserve a first look, but transients do not wait for embargo clocks, and cruise images that catch an interstellar visitor may never have been slated for papers. A practical fix is a standing fast track. Any dataset that could resolve an active, community-flagged transient moves to a rapid review lane with a target release window and a public status page. No drama, just a pipeline with a green, yellow, red dashboard that says whether frames exist, what stage they are in, and when to expect them. Chain of custody is next. You would not accept a courtroom photo with no timestamp or photographer. Do not accept mission images without raw headers, checksums, and version history. That is not an accusation. It is a standard. The same goes for ground observatories. If a claim hinges on a deep stack that reveals a faint skirt, the raw frames, calibration files, and processing scripts must travel with the claim. If the result only appears after aggressive sharpening, we rewind to gentle methods and see if it survives. Provenance is the difference between a striking picture and a scientific result. Now the loud question. What if multiple lines of evidence cross the gates we set for non-natural? We do not jump to a press conference, we widen the circle of verification. A pre-agreed verification protocol should name a small panel drawn from independent institutions with distinct instruments and no conflicts on this target. Their job is not to bless excitement, but to attempt to break it. They rerun pipelines, they pull parallel observations, they assess statistics and clock sync. They publish a short, signed report with a binary outcome on each gate: shape, chemistry, choreography, fields, custody, pass, fail, or indeterminate with reasons. National interests will loom. Space agencies answer to governments, and extraordinary discoveries trigger instincts far beyond science, security, prestige, public reaction. That is precisely why scientific transparency must be pre-negotiated. An international memorandum of understanding can carve out a narrow lane for observations of possible non-natural phenomena in near-Earth space. Raw data and essential metadata will be mirrored to neutral repositories under time-stamped escrow, to be unlocked once basic health and safety reviews are complete. Nobody is asking to disclose vulnerabilities or command codes, just the photons. Communication discipline matters as much as data discipline. Hype corrodes trust. Secrecy corrodes it faster. The right pattern looks like this. First, a methods note that announces the anomaly and the tests being run, with 0 grand claims. Next, rolling releases of reproducible plots and their raw ingredients. Finally, if the gates hold, a public technical brief that foregrounds falsifiable predictions for imminent follow-up. Every step includes null results, because nulls are the teeth that keep the work honest. Ethics enters as soon as artifact is on the table. If something looks engineered, do we attempt active probing radar chirps, targeted illumination, or close passes by assets in space? Not without a widely vetted protocol. Begin with passive observation until multiple independent signatures are secured. If active tests are proposed, publish the intended energy levels, frequencies, and expected interactions, and solicit international comment. Curiosity is not a license for reckless poking. Citizen science needs protections too. Community sleuths can surface decisive evidence, but they can also be targeted by harassment or misappropriation. Establish a simple code: public repos with clear licenses, credit lines that travel with figures, and open moderation spaces where disagreements are about data and method, never about people. A consortium's reputation is a shared resource, guard it. What if it all fizzles? Then we say so, fast and clearly. A transparent negative is a public good. It shows the pipeline works, that extraordinary claims can be explored without breaking trust, and that moving goalposts are not welcome. The next anomaly will arrive. The muscle memory we build now will make us faster and calmer then. This is the heart of evidence touching policy. Pre-commitment. Pre-commit to releasing raws with headers. Pre-commit to independent reanalysis. Pre-commit to calm language and testable forecasts. Pre-commit to publishing nulls. Pre-commit to time-boxed reviews so pending does not become purgatory. If 3i Atlas turns out to be a strange but natural traveller, these habits still pay off in cleaner science. If it pushes us to the edge of something new, these habits will be the only reason the world believes us. Zoom out for a moment. It is tempting to treat 3i Atlas as a lone oddball, but look at the wider sky, and you see a pattern. Over the last decade, we have built machines that watch everything, all the time in ways we never could before. Wide-field optical surveys scan the heavens night after night and flag anything that moves or flickers. Radio arrays keep a constant ear out for bursts and slow pulses. X-ray and gamma monitors patrol the high-energy sky. Gravitational wave observatories whisper when compact objects collide. Each new window adds a fresh stream, and the streams are full of surprises. That flood has a double edge. With more eyes, you find more anomalies. You also find more false alarms. Statistics get weird when you sift billions of data points. 1 in a million events happen thousands of times by pure chance. Instruments have personalities, and pipelines have quirks. A temperature drift can impersonate a dimming star. A cosmic ray glancing off a detector can masquerade as a flash. If you go hunting for oddities without discipline, you will drown in convincing ghosts. So, what is the antidote? correlation and replication. Correlation means different instruments, chasing different physics, reporting changes that line up in time and place. Replication means the same result turns up again when you look another night, with another telescope and another pipeline. This is not a mood, it is math. When independent streams agree more often than chance allows, you have signal. When a single instrument sings a solo nobody else can hear, you have a likely artifact or a discovery that still needs to earn its badge. This is why 3i Atlas is the right kind of problem for our era. We already have independent streams, optical profiles and infrared chemistry, polarization and deep imaging, radio and X-ray patrols that can be scheduled to overlap, even particle detectors that log time with ruthless precision. The tools are ready to run the correlation game properly. The only missing piece is coordination and a promise to publish nulls with the same pride as hits. There is another pattern worth noticing. The big weirds often shrink when we learn to measure the environment better. Fast radio bursts once seemed impossible. Now we see many of them, some repeating, and we have models that make testable predictions. Tabby's dimming star looked like it needed megastructures until dust with specific grain properties walked in with a better fit. Gravitational waves were once a rumor. Now they are a weather report that tells us when black holes and neutron stars merge. The lesson is hopeful. Weirdness is not a sign that science is broken. It is a sign that instrumentation and method have reached into a new regime where our first drafts are weak. But there is also room for genuine novelty. Every time we open a new slice of the spectrum or push cadence faster, nature hands us something we did not expect. Slow radio and X-ray pulses with clockwork timing. Neutrinos at energies that make particle physicists whisper. Interstellar visitors that play chemistry without showing a classic tale. The goal is not to domesticate every anomaly instantly. The goal is to build ladders strong enough that, if something truly new stands before us, we can climb carefully without falling for illusions. That takes culture as much as hardware. A culture that rewards careful negatives, that celebrates replication more than rhetoric, that treats community dashboards and open code as first-class outputs, that refuses to move goalposts when a favoured idea does not survive contact with data. The internet age can amplify noise, but it can also amplify method if we choose it, so the big picture is clean. We live in an era where the sky talks constantly across many channels. Big weirds are not bugs. They are the price and the prize of listening so well. Some will fade into better calibrated normalcy. Some will mature into new chapters of physics. 3i Atlas sits at that fork. If it is a quirky comet, we will prove it the modern way, with overlapping streams that agree. If it belongs to a stranger family, we will not get there by hot takes, but by the same streams locking into patterns that chance cannot fake. Curiosity can run fast. Proof must run faster. That is how the pattern turns into progress. A mystery gets solved faster when everyone knows exactly when to look and what to look for. That is why we are building a public observing calendar for 3i Atlas, and not a vague wish list, a living schedule with dates, hours, and targets that anyone from a backyard rig to a national observatory can use. The recipe is simple. Put the geometry on a clock, put the physics on a checklist, then let the crowd move in formation. Start with the ephemeris, the object's appointment book. We post nightly positions with uncertainty cones and a simple finder chart so small scopes can hop there easily. Right beside that, we list the phase angle for each night, the Sun-Object-Earth triangle that decides whether a tail would be foreshortened or fanned out. We color-code it. Narrow angles in blue, middle angles in amber, generous angles in red. If geometry can hide a tail, those colors show when the excuses run out. Next, schedule the tests in plain language. Polarization runs, get the nights with steady phase angle progression, ideally 3 to 5 samples spread over 2 weeks. Deep imaging gets the calmest seeing windows just after the moon departs, with 2 filters per session, a dust-friendly continuum and a nearby gas-sensitive band. Light curve watches run almost every clear night, but we flag 3 relay nights per rotation campaign, where a chain of small telescopes hands off coverage across longitudes, so we can capture at least 1 full spin with minimal gaps. Infrared spectroscopy slots in wherever a facility has time, but we anchor a few 1-hour blocks that overlap the deep imaging and relay watches. Radio and X-ray. Partners mark listening windows that shadow those overlaps with sub-minute cadence. The point is not perfection, it is synchronized opportunity. Then we staple in the environment. The calendar carries a space weather lane that shows geomagnetic forecasts, solar wind speed, and any active alerts. If a storm is inbound, we do not cancel, we tag the session, storm mode, and plan extra calibration, plus a quiet repeat on the first calm night that follows. We also add a seeing tracker for key sites and a cloud map link for the next 12 hours so people can call audibles without guessing. Every session page gets a box that says what counts as success that night, a radial profile deeper than last week, a polarimetry point with a stated error bar, a light curve segment with a minimum time span, a spectrum that covers specific water and carbon dioxide lines. Clarity beats hype. Submission is lightweight by design. You upload 3 things: a quick look plot, the raw or minimally processed data in a standard format, and a one-line conditions note. For images, include a profile against a nearby control star. For polarimetry, include the calibration star you used and the measured instrumental polarization. For light curves, include the comparison stars. For spectra, include the wavelength solution residuals. Each upload auto-stamps time, instrument, filter, exposure scheme, and pipeline version. That metadata is gold. It makes your work stackable with someone 2 continents away. We also keep score, openly and kindly. A dashboard shows progress against the hypotheses. Microvent World wants to see a profile shoulder that grows with gas strength. Fragment Swarm wants a slightly irregular light curve and a drifting elongation angle. Field Corral wants non-comet polarization or radio whispers that correlate with optical changes. Rotation Control wants phase-locked gas pulses. Chemistry First wants stable carbon dioxide to water ratios while dust remains scarce. As data, there arrives, small tick marks fill the lanes. No verdicts based on one night, just accumulation. When a lane meets its pre-registered target twice, a banner appears. Replication achieved. When a lane repeatedly misses, we grey it out. You feel the investigation tighten in real time. Everyone gets a role. Big facilities win on depth and precision. Small scopes win on time coverage and nimbleness. If you have a 60mm refractor and a decent camera, you can still contribute to the light curve relay with 30-second exposures and careful calibration. If you run a school observatory, polarimetry in 2 colors at 3 phase angles is a semester project with scientific bite. If you love code more than clouds, help write the autoprofilers and sanity checks that flag likely artifacts. If your superpower is coordination, run the nightly huddles and keep the handoffs clean. We will also hook into always-on partners. Neutrino and cosmic ray dashboards will be scraped for event times. The calendar will flag any coincidences with observing blocks, not as claims, but as prompts to check the clocks. Magnetometer stations will feed a live strip chart, so we can annotate frames with actual particle noise rather than guesswork. When something odd appears, a one-click ping rallies the overlapping facilities for a fast follow in the next available hour. 2 final promises make the calendar worth your time. First, we publish nulls alongside hits. A deep stack that shows nothing is still a tile in the mosaic. It sets limits that sharpen the picture. Second, we lock in release windows. Quick look plots within 24 hours. Raw bundles within 72. Cleaned and documented stacks within 7 days. No hoarding, no mystery gaps. The calendar is not a billboard. It is a mission plan we can all read. With it, the investigation stops being a sequence of isolated stabs and becomes a rhythm section. When the rhythm is tight, answers appear. If 3i Atlas is just a strange chemistry case, the calendar will prove it cleanly. If it is walking us to the edge of something new, the calendar will be the road that gets us there, without getting lost. Lace up, pick a night, bring a plot. We will meet you on the timeline. Here is where we turn the plan into a clock, 90 days. That is enough time to move from chatter to clarity, if we keep the pace and keep the rules. Day 1 is not a pep talk, it is a checklist. By the end of this run, we either have a clean, natural story for 3i Atlas, or a tight bundle of anomalies that demand the next tier of tests. No drama, just work. Days 1 through 10 are the archive sprint. We finish the Psyche windows with final ephemeris cross-checks, then file precise requests for any frames that could hold the target. We mirror the requests to neutral repositories, so timestamps travel with them. In parallel, we scrape ground observatory indices for engineering frames and calibration sweeps taken during the same nights. Every candidate frame gets a checksum, a quick difference against a template starfield, and a note in the public log. If nothing surfaces, we declare that early and free up attention. If even one usable frame appears, we ship it to 2 independent teams for blind reduction and point spread subtraction. Results go on the board within the week. Days 11 through 30 are for deep imaging and polarization. We stack hard on 2 moonless runs with the largest mirrors we can book, while smaller scopes build redundancy. The rule is simple. 2 filters per night, 1 continuum for dust, 1 near strong gas features, align on the target, subtract a matched star, and post the residual. Right beside it, we add the polarization points at the same phase angles with their calibration stars and error bars. By day 30, we expect one of 2 things. Either a faint, repeatable shoulder appears that tracks with gas, or profiles remain star-tight through generous angles. Either answer is progress. Days 31 through 50 are the light curve relay. Small telescopes carry the baton around the planet on 3 selected nights to capture at least 1 full rotation each time. We fix exposure times in advance, fix comparison stars, and write down sky conditions in the caption of every segment. Then we fold the curves to test periods and look for repeatable bumps. If gas logs exist for the same nights, we phase them with the curve. A linked bump means geography. A smooth curve without quirks means unusual uniformity. A messy curve with no period means tumble or short-term bursts. We do not guess. We plot and label. Days 51 through 70 run the coordination test. We pick the best geometry window in this block and throw the kitchen sink at it for 1 night, then again a week later. Infrared watches the water and carbon dioxide lines on a loop. Optical stacks push deep and post profiles in near real time. Radio listens in sub-minute bins. X-ray snapshots hop through the night. Space weather and magnetometers stream along the bottom of the dashboard. We pre-register the coincidence window and the false alarm rate. At sunrise, the logs already tell a simple story. Together or not, repeat or not, days 71 through 90 are for audit and synthesis. 2 teams reprocess the top datasets with alternate pipelines. 1 team publishes the statistics on all claimed correlations with the pre-registered windows, not the ones that fit after the fact. 1 group writes the chemical timeline from all spectra, with uncertainties that include calibration drift. 1 group writes the shape timeline from all profiles with seeing folded in. Everyone posts nulls. Everyone posts code. Everyone posts raw bundles. No mystery folders. We set 3 finish lines and promise to honor them. Finish line 1 is natural with a twist. That happens if deep imaging shows a repeatable compact skirt tied to gas. Polarization lands on the comet family even if muted, and the light curve shows a period with quirks that line up with vents now and then. The headline then is a dust, shy interstellar comet with an unusual pantry and rough weather. That is a worthy ending. Finish line 2 is exotic natural. That happens if profiles stay star-tight, yet polarization refuses the comet family across phase angles, and radio or X-ray instruments catch faint murmurs that repeat near gas surges. The headline then is field-sculpted dust and plasma around a small body, a door into physics we have not mapped in this regime. That calls for more polarimetry, more radio, and maybe a dedicated small mission in the future. Finish line 3 is the one that tightens your throat. That happens only if edges hold at the limit of resolution across visits. Polarization pops at angles that speak of facets, multi-band timing locks like gears more than once, and custody is clean with raw frames and checksums for every critical plot. If we cross that line, we do not sprint to microphones. We trigger the pre-agreed verification panel, hand them the raws, and let them try to break it. If it does not break, the world will hear from many voices at once. Across all 3 lines, we keep a single promise. We do not move goalposts. If the object behaves like a comet in our best data, we say so, and celebrate the craft that proved it. If it behaves like something we have not seen, we say so with humility, and the tests that anyone can repeat. 90 days is not a magic number. It is a posture. It says we can do hard things quickly when we are organized. It says the method matters more than the mood. It says the sky does not owe us a headline, but it will reward our discipline. Let us finish the run. This is where all the threads tighten. We began with a paradox that should not fit inside one sky, an object that breathes like a comet but draws itself as a perfect point. We built tests instead of takes. We set gates that even a skeptic would accept. We drew a 90-day clock and filled it with actions, not adjectives. Now we close the loop, not with a prediction, but with a promise. The sky will answer if we keep our method clean and our nerves steady. First, what we already own: deep stacks that behave like rulers, infrared lines that do not care about hype, a calendar that forces geometry to stop hiding. Polarization runs that turn texture into plots instead of metaphors, light curves that give rotation a voice, coordination nights that stitch all of this together with synchronized clocks. None of these alone is a verdict. Together, they are a lie detector for stories that try too hard. So here is the final frame for truth. 3 decisions, each tied to measurements we can make on ordinary nights with extraordinary discipline. Decision 1. Dust or no dust. If a compact, repeatable shoulder appears after point spread subtraction and grows with gas production, dust is present, and the no-tail was a phase of timing, grain size, or crust. The paradox collapses into a natural story with an interstellar accent. If profiles remain star-tight through generous phase angles and quiet seeing, the dust deficit is real and requires either unusual materials or forces that keep grains close. Either way, the shape stops being a rumor and becomes a measurement. Decision 2. Chaos or choreography. If gas, light, radio, and X-ray stroll past each other without keeping time, chemistry runs the show, and fields do not deserve top billing. If, instead, we catch repeated nights where a gas surge lands within the same tight window as an optical, softening and a timid radio flutter, choreography is on the table. Repeat it, and plasma becomes part of the play. That does not make the object artificial. It makes it interesting for physics we rarely see in this regime. And if the choreography refuses to break under independent pipelines and pre-registered statistics, we move it up from interesting to important. Decision 3. Lumpy or made. If deep, imaging at the limit of resolution resolves edges that keep their angles as the viewing geometry changes. If polarization pops at phase angles that scream facets rather than fluff. If timing across bands locks like gears and not like weather. And if every plot travels with raws, headers and checksums, then we have crossed our own gates. At that point, the process takes over. The independent panel tries to break it, and the world learns whatever survives that pressure. No breathless leaks, no coy hints, just receipts. You may feel the tug to decide now. Resist it. We built this documentary as a shared investigation, not a guessing contest. The satisfying ending is not a twist. It is a standard held so high that any outcome quirky comet, exotic natural, or something we do not have a word for yet, sits on rock instead of sand. That is how you earn the right to be surprised without being fooled. There is also a deeper reason to finish well. This is not only about one visitor. It is about how we meet the next big weird without tearing our trust in the process. The calendar we wrote is reusable. The dashboards are reusable. The culture of public nulls and fast raw releases is reusable. Instruments age. Habits endure. If we can show that a sprawling global crowd can run a hard case with professional calm, then the next anomaly on the sky, in the lab, anywhere, arrives into a field that is already trained to separate signal from story. So, where do you stand in the last act? If you have a telescope, you stand under the dark and add a clean point to the light curve relay. If you have access to a big mirror, you stand at the focus with adaptive optics, hunting that faint shoulder inside the blur. If you run code, you stand in the pipeline, writing simple, transparent tools that anyone can rerun. If you teach, you stand in front of a class with a polarimetry project that will outlast this season's headlines. If you just love the hunt, you stand in the comments with questions that make plots better and conspiracies smaller. And yes, you are allowed to enjoy the drama. Mystery is the music. Method is the meter. We moved from a gasp to a plan. From a plan to measurements. From measurements to decisions that do not care about mood. Somewhere on a night not far from now, a profile will either bend or it will not. A polarization curve will either land on the comet family or it will not. A stack of clocks will either tick together or they will not. The beauty is that any of these answers is a win, because each one pulls a layer of fog off the same horizon. When that horizon clears, we will tell you plainly. If 3i Atlas is a dust-shy interstellar comet, we will show the stacks and the curves and close the case with gratitude for a universe that keeps stretching our models. If it is a small laboratory for field-sculpted dust and plasma, we will map the choreography and ask for more instruments to listen. If the gates we set swing open in unison and nothing natural can pass through them, we will walk right up to the line we drew, together, and announce what the data leave us no choice but to accept. Until then, keep your curiosity sharp and your standards sharper. Tap subscribe so you do not miss the coordination nights and the final plots. Share the calendar with anyone who can add a clean point to a clean figure. This is how we settle not just this story, but the way stories like this will be settled in the years ahead. The sky owes us an answer. We owe the sky our best craft. Let us finish the work.